Hey, what's up, guys? This is Cheng here again. So this time, LeetCode 1944, number of visible people in the queue. This one, it's I wouldn't say it's a hard one. It's a medium, more like a medium one. So we have n people standing in the queue, right? And they numbered from 0 to n minus 1 in left to right order. And you're given like a height of distinct integers, right? Basically, each person have a different height. And the person can see another person. But we got a bunch of minions here. A minion can see another minion to their right if in the queue, if everybody in between is shorter than both of them. Okay, so this is a more formally explanation. So the person can see this person if I is smaller than J, and anything, basically there's no block between those two persons, right? And our task is to return like an answer of length of n, where the number of people of the ith person can see to their right in the queue, right? So for example, we have this bunch of minions with different heights, right? So, and then the output is 3, right? The output is like 3, 1, 2, 1, 1, 0. This is because, for the first minion, right, it has height 10, right? So how many minions can see? It can see this one. This one is fine. This one is fine, but this one is not, because obviously, because this one is blocked by this minion, right? But this one can see this one because this one didn't didn't get blocked. Same thing for here, right? And also this one, right? But not this one, because this one is also blocked by this one, right? So that's why we have 3, right? And then the next one is what? The next one is 1. So for this one, for the second minion, the answer is 1, because this one can only see this one. There's nothing more, because all the others, they're all being blocked. Even though, right? I mean, even though this one is higher, but even though this one is this high, but I think we didn't count that, because the definition is that, in order for this person for this minion to see to this minion, all the minions in between has to be smaller, has to be shorter than any of them, right? That's why the answer for this one, for the second minion, is 1, right? And then for the third one, right? For this minion, it can see this one, right? And then it can also see this one, but not this one, right? Because this one has been blocked by this one, right? Similarly, as you guys can see, right? So at least the minion can see its neighbors on the right side. Similarly for this one, right? So for this one, it can only see this one, right? And then for this one, right? It can see this one, but there's nothing here. That's why it's also 1. For the last one, obviously it's 0, right? And yeah, that's it, right? I mean, the 10 to the power of 5 and all the values of heights are unique. Okay. So this one, I mean, so for this problem, obviously the brute force way is that for each of the minions, right? For each of the minions, we loop through to the right side, right? And then we loop through everything, right, to the right, until we have seen a one that is greater than the current one. For example, right, if from 10 we loop through to the right side until we have seen we have reached the 11, right? No, sorry. I mean, from 10 we loop through everything to the right side. Okay, so every time there's like, let's say for 6 is fine, but for 8, right? For 8, 8 is fine. 8 is fine, but for 5 is not, because basically we're maintaining the previously highest minion, right? And then we only accumulate the answer when the current one is greater than the previous one, right? For example, when the 6, then the highest is 6, when it's 8, the highest is 8, right? But then the 5, when 8 is greater than 6, that's why the 8 is fine. But when it comes to 5, 5 is smaller than the current highest, which is 8, that's why 5 is not. But 11 is fine. 11, because 11 is greater than 8, but now 11 is the current highest, and then 9 is not, right? So which means obviously we have to, for each of the meanings, we have to do a O(n) scan, right? It will be a n squared time complexity. So for this one, the easiest way to do it is to simply use the monotonic stack. I think, is it stack or queue? I think it's monotonic stack. So which means in this one, actually, all we need, we need is it increasing or decreasing? Let me think. I think it's going to be an increasing queue, increasing monotonic stack. It's because, okay, so how do we use that to help us solve this problem? So first, in order to do that, we have to loop through from the end to the start. Because as you guys can see, right? So the first one is 9, right? The first one is 9. The second one is 11. If we loop through from the end to the start, since 11 is greater than 9, right? So what does it mean? It means that it doesn't really matter how many meanings on the left side, and none of them will be able to see 9 anymore, right? Because there's like 11 on the left side, which will always block the 9, right? Similarly for we have 10, 6, 8, 5, 11, and 9, right? Similarly for this 5 here, let's so for 5, right? I mean, we have 8 on the left side of 5, right? So what does it mean? It means similarly, what, anything on the left side will not be able to see 5 because 8 it's blocking standing in front of 5, right? So which means that every time if we loop through from the right to the end to the start, every time when we see if the current height is greater than the previous one, we can simply remove it because that's not useful anymore, right? We can simply remove it. That's why this is like the perfect candidate for the monotonic stack, right? So what does it mean? It means that like this. So first we have 9, right? So we have 9 in the monotonic stack, which is the increasing stack. And when the 11 comes, so 11, see, okay, 11 is greater than 9, right? That's why we're gonna move this one out. So now we have 11 here, okay? And then we have 5, right? So 5 is smaller. 5 is smaller. It's not greater than 11. That's why we're gonna keep increasing, pushing it to 5, right? And then the 8 comes. So when 8 comes, 8 is greater than 5, right? So we're gonna remove this one and we're gonna push 8 here. And then 8 is smaller than 11. That's why we're gonna keep this 8 here, right? And then we have 6, right? 6 is smaller than 8. That's why we keep it there. And then we have 10, right? 10 is what? So 10 is greater than 6. So 6 is out. It's greater than 8. 8 is out. But 10 is smaller than 11. That's why we're gonna put 11 here. We're gonna put 10 here, right? And then as you guys can see, actually the number of the people the current person can see has a very close relations between the numbers that got popped from this monotonic stack, right? For example, this 10, right? So remember we have 8, we have 6, and now the 10 comes, right? So 10 will pop 6 out, right? And then we'll pop 8 out, right? That's why we have 2 here, right? And then we have 11, right? So this is third one, because 11, even though 11 is not gets popped, but the 10 can see 11, right? So I think that's pretty much it is, right? So basically we simply maintain like a monotonic stack, and then we count how many numbers got popped out, because as you guys can see, this 5 will not be counted, right? Because 5 have already been popped when the 8 got pushed into this monotonic, the increasing stack. That's why you know that 5 is not counted for this minion has height 10 here. Only the 6, 8, and 11, right? And yeah, so for the implementation, it's pretty increasing stack. Maybe I'll just call it this one. And then we have n is going to be length of height, right? And the answer is going to be this. Okay, and then we loop through from the end, right? N minus 1, minus 1, and minus 1. We have a total, maybe. So while increasing stack is not empty, and the height of the current one is greater than the increasing stack of minus 1, right? Because this one is the top one, right? And then we increasing stack dot pop, okay, and then we increase the total plus 1, okay, right? So and then another one is that if the increasing stack is not empty, we will basically increase the total by 1, right? So this one is for what? For the next for the person, right? For the count the person who is higher, right, than the current one, right? Because for example, for 10 here, right? So for 10, we pop 6, we pop 8, and then we have 2 here. But the answer is 3 because we have 11. 11 here, this current person can also see. But the reason we want to do this separately is because, for example, for the 11, right? For the 11, once when the 11 comes, it will pop 9 out. That's why the total is 1, right? But the answer for 11 is 1 because there's no more minion left in this increasing stack here. That's why we have to do it increasing the total separately. Only when there's still some minion left, higher minion left in this increasing stack, right? And then we push this increasing stack with the current height, right? And then in the end, simply we update the answer, right? With current total, right? And then return the answer. That's it. Okay. Submit. Yep. So that's it, right? I mean, uh, it's pretty straightforward. I mean, I don't know why they rate this one as hard. Maybe because of the use or the idea of using increasing the monotonic stack. It's not that common, right? But yeah, regardless, I think it's a very necessary or a very useful technique everyone should know, right? Basically, the reason we use a monotonic stack is that we will not reprocess this useless minion multiple times. For example, this 9, this 5, this 8, right? So which means that each of the minion will only be pushed and popped in and from this monotonic stack once. That's why the time complexity for this one is O of n, right? Yep. And the reason we can use the increasing stack is because, like I said, anything that's after on the right of this higher minion will be totally useless because it will be completely blocked by this one. That's why we can safely discard this one. right? Because of that, we chose to use the monotonic stack. And okay, I think that's it for this one. And thank you for watching this video, guys, and stay tuned. See you guys soon. Bye-bye.